It's great pleasure to have Yang Li with us, who will be telling about Equivariant Lagrangian Correspondence and a Conjecture of Teleman.
Okay, so morning everyone. So thank you for coming, and thanks for also an invitation for me to speak in here. So today I'm going to report on a joint work with Siu-Cheong, who should also be here maybe, and my advisor Conan Leung, based on our preprint with the same title as the talk. And I'm going to talk about Conjecture of Teleman, which concerns about mere construction of Hamiltonian G-manifold and its symplectic quotients, and in which our main techniques will be the Equivariant Lagrangian Correspondence. Okay, so let me go ahead to recall what is a Hamiltonian G-space. So Y will be a Hamiltonian G-space, which means Y is a symplectic manifold together with a Hamiltonian G-action for a compact Lie group G, together with a moment map mu mapping to the Lie algebra dual, which the moment map means it is G equivariant and it satisfies the Hamiltonian equation of this form. Okay, so because we want to discuss the symplectic quotient, so we assume following. We assume that G acts freely on the moment map level 0, which in particular implies 0 is a regular value of mu, which implies mu inverse 0 is a smooth submanifold of Y. Therefore, it's a submanifold which G acts freely, so it has a smooth quotient, which we denote it by X. And the classical theorem, independently by Marston, Weinstein, and Mayer, is that such an X emits a natural symplectic form omega bar, such that its pullback along this natural projection pi is equal to omega restricted onto the level set. Such an X together with such an omega bar is called a symplectic quotient or symplectic reduction. So a natural theme that have been occurring in the past decades is to compare the G equivariant geometry and topology of Y and the geometry and topology of X. And today I'm going to discuss also in this direction in terms of Lagrangian Floer theory. So let me further enhance the setup. So given the Hamiltonian G-manifold as before, but now we also consider a Lagrangian L, which is G invariant, which means G acts on L. Together, we will assume something more. We assume also it's closed and connected and so on. So as a matter of fact, given such a G-invariant Lagrangian, it always sits inside a moment map level for some central constant C. So therefore, since C is central, so we can shift this mu by mu minus C, so that we can, without loss of generality, assume that C is 0. Therefore, in this case, L lies inside mu inverse 0, in which we assume G acts freely on mu inverse 0. Therefore, G in particular, G also acts freely on L, so that its quotient will be a submanifold in X, which we denote it by L bar. And it turns out that this L bar is also a Lagrangian in X, which we call a Lagrangian quotient. So a goal for the paper, which we will discuss some in our talk also, is to, first of all, we want to define a version of G equivariant Lagrangian Floer theory of such a G invariant Lagrangian L in Y. And not just giving a definition, but we also want to compare this G equivariant theory with the Lagrangian Floer theory of the Lagrangian quotient L bar in X. Okay. But of course, you might ask, so why should we be interested in this? So our motivation is coming from the following conjecture by Teleman in his ICM address, but we restrict to the case that G is abelian temporarily for simplicity. That's what it asserts is the following. So mirror of a Hamiltonian T action would be a holomorphic vibration F defined over the mirror space of Y mapping to the complexified dual torus. So he claimed that mirror of Hamiltonian action is such a holomorphic vibration with the property that the fiber at 1 respect to this F gives a mirror of Yx. So where X is the symplectic quotient of Y. Okay. Moreover, if the mirror is not just a space, but is a Landau-Gisbert mirror, namely a space Y check, together with a so-called Landau-Gisbert potential W defined as a holomorphic function defined on the mirror space Y check, he further asserts that the restriction of the potential onto the level set gives the Landau-Gisbert mirror of X. So this is his conjecture. So let me let me give the following remark first. So there are some ongoing works considering some closing version of this conjecture by Teleman himself, together with Pomeriello, in terms of equivariant quantum cohomology or symplectic cohomology. And also there are some ongoing work by Eritani and Sander in formulating this in terms of quantum D modules. Okay, but in this talk or in our preprint, we will be discussing the open string version of this conjecture. And moreover, you might ask, so why Teleman gives this conjecture? A quick answer is that it generalizes the Givental-Hori-Vafa mirror symmetry for toric varieties, in which we will give an example very soon. But on top of it, there's also a deep reason for giving this conjecture. Is actually this conjecture arises from some version of a 3D mirror symmetry. But because of time limit, I won't be able to explain more about this point of view. But in case anyone is interested, I'm happy to discuss more maybe in the discussion session. Okay. So I've stated the conjecture. So let's see some example of it. So a typical example of it is consists of the class of toric varieties, in which first of all we discuss CP2 as a symplectic quotient of C3 by the diagonal S1 echelon of this form. Then the so-called Givental-Hori-Vafa mirror construction for toric varieties says the following: the mirror of C3 is the Lagrangian model C star 3 together with this potential function Z1 plus Z2 plus Z3. The mirror of this diagonal S1 echelon is the holomorphic vibration given by Z1 times Z2 times Z3, mapping to C star. So the mirror construction says that the fiber as so I fix a particular constant C here, then it corresponds to the level as e to the power C here. Then the fiber at this level is of course it's just like nothing but a copy of C star 2. For example, we can choose C1, C2 as coordinates. Then when we restrict this potential upstairs to this hypersurface, then it has a form Z1 plus Z2 plus e to the power C divided by Z1, Z2. And this is called a Givental-Hori-Vafa mirror of P2 with this respect to this scalar form. Okay. So, okay, this is the construction, but actually, this can be understood from Lagrangian Floer perspective. So now we consider a Porter Lagrangian torus inside C3, which lie inside this level, so that S1 at all. So that when it has an S1 echelon and its quotient will be a Lagrangian torus fiber over this moment polytope of P2. Okay, and it's a theorem by Cho and Lo that this mirror can be understood as the mirror the so-called localized mirror associated to this L bar, which means it can be realized as a Riemann-Cartan space of L bar, which is a formal deformation space of L bar. So it's called Riemann-Cartan space, together with this potential L bar, which roughly speaking is the count of the mass of two disks. And they show that this mirror can be understood as the localized mirror in this sense. And also for upstairs, the C star 3 can also be understood as a Riemann-Cartan space of T3 with this potential equal to the superpotential. And geometrically, these three terms correspond to the so-called basic disk bounded by the Lagrangian torus fiber, which in this case, each basic disk corresponds to each toric divisor. So in P2, there are three toric boundary divisors. So it corresponds to three classes of disks, which are called basic disks. And these three terms exactly correspond to these three basic disks, which are the mass of two disks bounded by this Lagrangian torus fiber. And more generally, it can be generalized to when Y is CM with the linear subtorus action, and X is a symplectic quotient, which by definition is a toric variety, which is also assumed to be compact toric Fano. Okay. You may ask, so whether this Fano assumption is important, and it turns out it's important as the following example suggests. So the following is an example of a second Hilbert surface, which its potential is first computed by Oru and later generalized into comparator varieties by Fukaya, Ota Uno, and Kim-Lau-Zheng in the semi-Fano cases. So in this case, Y is C4 with this particular linear subtorus T2 action, and its quotient is the so-called second Hilbert surface, which has the moment polytope like this. And it is a semi-Fano surface, which in this case is this semi-Fano, meaning the effective curve has a non-negative Chern number. And in this case, it has the exceptional divisor has 0 Chern number, and this 0 corresponds to that is semi-Fano. And we also consider the Lagrangian torus fiber as before. But in this case, the mirror has more than the number of terms than the Givental-Hori-Vafa mirror. So the mirror, the Lagrangian Floer mirror, has 5 terms in which the first 4 terms correspond to the basic disk that I've just explained in the previous example. So one Toric final divisor corresponds to one basic disk. So we have 1, 2, 3, 4 correspond to these 4 terms. And the Givental-Hori-Vafa potential will have these, we consider these 4 terms. However, in this case, because of the Chern zero sphere, so it causes the source interior sphere bubbling together with interior sphere bubbling with respect to this basic disk, so that we have the 5th disk. So therefore, we have so the Lagrangian Floer potential have 5 terms instead of 4 terms that were predicted by the original construction by Givental-Hori-Vafa. So therefore, they are not equal. So these 2 potentials are not equal. So it seems that there's some problem, some trouble concerning this example. But our interpretation is like this. So the Lagrangian Floer potential and Givental-Hori-Vafa potential are off by this term, this particular 5th term. And we understood it as the following, that so the Lagrangian formula correspond to this potential of L bar. The Givental-Hori-Vafa mirror potential correspond to this potential up on L restricted onto a fiber of 1 as before. However, there's some extra terms that comes from the so-called obstruction that can be explained by obstruction terms bounded by the moment level. Of course, this statement sounds vague, so okay, so this is time for me to explain our results, to explain what this actually means. So the setup of our main theorem is as follows. So this is the general setup. So now we return to the Hamiltonian G action case again with a smooth symplectic quotient as before, and we've considered a Lagrangian, which is G-invariant Lagrangian lying inside mu inverse 0 with the quotient Lagrangian quotient L bar. So we have these 2 Lagrangian. Moreover, we have the following Lagrangian correspondence. So if we have L pi, which is defined to be graph of this the natural projection pi, but we consider it as a submanifold of Y cross X. And it follows by definition that it is a Lagrangian of Y cross X, where the Y have a negative symplectic form. And this is called the moment level correspondence, which a Lagrangian correspondence is nothing but Lagrangian inside this product symplectic manifolds. Moreover, is G invariant, so G equivariant, which G acts on Y cross X. So it acts on Y by definition and acts on X trivially. And this action reduces an action on L pi, which makes it a G equivariant Lagrangian correspondence. And this will play a very key role in our formulation of our theorem, which is stated as follows. So this is the first part of our theorem, is we have a notion of we construct a version of an equivariant Floer complexes, which is in particular an A-infinity unitary A-infinity algebra over an oblique ring. So that's the underlying module. So this CFG of L, the underlying module is the classical equivariant cohomology. Okay. And so this is our first construction. And using this A-infinity algebra, we can define the Riemann. So we can consider is Riemann-Cartan space, which we call it the equivariant Riemann-Cartan space of L, which by definition is consists of an odd degree positive valuation element in this A-infinity algebra, such that it satisfies the so-called Riemann-Cartan equation, which has this form. And by its very definition, there's a multiple here, multiple of the units here. And this multiple defines a function on the equivariant Riemann-Cartan space, which we call it the equivariant dispotential. So this is the WG of WGL. So we have this for L, but we also have this for L pi by the same reason. So instead of L, we consider the Lagrangian to be L pi, and then we can have is equivariant Riemann-Cartan space and is equivariant dispotential. Okay, so but you might ask, so what does this good for? So we can compare it with the flow theory of the Lagrangian quotient as follows. So this is the second part of our theorem. That's for each equivariant bounding cochain of L pi, which we call B pi. We have so given such a B pi, we have a bijection between the equivariant Riemann-Cartan space of L with the Riemann-Cartan space of L bar, such that for each pair B and B bar under this bijection, their equivariant dispotential satisfy the following identity. So the equivariant dispotential of L bar of L on B is equal to the W of L bar of B bar with the off by a term that is the equivariant dispotential of L pi on B pi. And this is exactly the ... that appeared in the previous slide. So we have an identity of the equivariant dispotential. And this play a key role in our formulation of the so-called localized Teleman's conjecture for abelian group G as follows. So first of all, I recall a fact which was proved by Kim-Lau-Zheng using a so-called equivariant Morse model to define another version of another notion of an equivariant equivariant Riemann-Cartan space of L, which denoted like, so we have tilde here. So that the dispotential is equivariant dispotential is linear over equivariant coefficients. So sorry, I should say the A infinity algebra is linear over equivariant coefficients. So that this equivariant dispotential value over equivariant coefficients, and its equivariant part defines a function which I call FL to the lambda cross k to the power k. So that's so this is their construction, and we can show that its fiber as one, I can be identified with the equivariant Riemann-Cartan space that I've just defined. And moreover, the restriction of this equivariant dispotential onto the fiber of one can identify with the equivariant dispotential that I've just defined in the previous slide. Now, combining this with our theorem 2, then we can conclude that this can identify with the equivariant with the Riemann-Cartan space of L bar, so that we have such an identity of the equivariant dispotential. So altogether, it is an open string version of Teleman's conjecture, but with the extra ingredient that such an extra term appear. Okay. And more generally, we can instead of so it's just a quick remark that instead of assuming B pi is a equivariant Riemann-Cartan element, it can be the equivariant Riemann-Cartan element with respect to equivariant Morse model, such that its F is not 1. But I won't have time to explain more on this, but this will be necessary to handle the semi-Fano Toric semi-Fano case. But just put it here so that we can do something more general than this. Okay, so let's return to the Toric variety example. So, by the way, I still have like 1 minute or something.
You do have 1 minute, yes.
Okay. Then we can do something on Toric variety. So in last minute, let me jump to where is the equivariant Lagrangian correspondence. So, okay, so we have the same setup before, but we consider L pi as a equivariant Lagrangian correspondence that map L to L bar. But using this, we do an equivariant symplectic Borel construction, so that we get the same picture, but we replace the Y by the so-called the symplectic Borel space and Lagrangian by the Lagrangian Borel space. But with same picture, and this picture allows us to so that we can consider its so-called equivariant correspondence trimodule, which is an equivariant extension of Fukaya's correspondence trimodules, such as with a so-called equivariant cyclic element that allow us to compare the Riemann-Cartan spaces of L bar and L, which implies our theorem 2 with the desired identity for the slope potential. But okay, I'm running out of time, so let me end here. Yep. Thank you for your attention.
Okay, let's thank Jan for this talk. Any quick questions for Jan? We will have a discussion at the end. Arthur, do you have a question? Go ahead.
Oh, sorry, I wanted to clap. That was a mistake.
Oh, okay. No worries.
Oh, okay.
Any quick questions for Jan?
Can you quickly comment on this this remark you made about how it connects to the 3D mirror symmetry? Sorry.
Yeah, the relevant to 3D mirror symmetry is a ratio of 3D mirror symmetry is considering the category of boundary in terms of category of boundary conditions. But in the 3D case, if instead of just a category, it forms a two category, and there's two categories, and there are some conjecturally there are some two categorical equivalents between them, and one of the examples that Teleman proposed is in terms of gauge theory, and so in the gauge there's some 3D mirror pair given a G action, we have a two holomorphic symplectic stack, so that there's some category boundary condition on it, and there's some two category equivalents of it. And if we, of course, well, although it's conjectural, but if we study some particular simple object and consider their morphism space, and then we can, one of the examples that will give rise to the Teleman's conjecture. Yeah. So this is, well, of course, I didn't explain in detail, but a quick answer would be like this. But I'm happy to say more in the discussion.
Okay.
Very good. Okay, let's thank Jan again, and then